Piping vibration, mechanical excitation, understanding causes and effects of piping vibrations. Introduction to piping vibration, significance of piping vibration in process systems. Piping vibration is a critical issue in process industries because it can lead to fatigue failures, leaks, and catastrophic ruptures, posing severe safety, environmental, and economic risks. Mechanical excitation is one of the most common sources of vibration, particularly in systems involving rotating or reciprocating machinery. Unlike flow-induced turbulence, which is broadband, mechanical excitation typically introduces tonal energy at discrete frequencies related to machine operating speeds and their harmonics. When these frequencies coincide with the natural frequencies of piping spans or small bore connections, resonance occurs, amplifying vibration levels significantly. This phenomenon can cause high cycle fatigue damage at welds, supports, and connections, leading to premature failure. Understanding mechanical excitation is essential for engineers to design robust piping systems, implement preventive measures, and comply with industry standards such as API 618 and API 674. The consequences of neglecting vibration control include unplanned shutdowns, costly repairs, and potential hazards to personnel and equipment integrity. Definition and mechanism of mechanical excitation, how mechanical excitation occurs. Mechanical excitation refers to dynamic forces transmitted from machinery into connected piping systems. These forces originate from unbalanced reciprocating masses, cyclic pressure variations, and structural vibrations of the machine itself. Reciprocating compressors and positive displacement pumps generate periodic forces due to their operating principle, where pistons or plungers create alternating pressure pulses. Rotating equipment such as centrifugal pumps and compressors can also induce vibration through imbalance, misalignment, or rotor dynamics. The excitation energy is tonal, meaning it occurs at specific frequencies, typically the machine's running speed and its harmonics. If these frequencies align with the piping's natural frequencies, resonance amplifies the vibration response. Structural coupling through shared supports or skid frames can transmit vibration to adjacent lines, even if they are not directly connected to the machine. This mechanism underscores the importance of analyzing both the excitation source and the piping system's dynamic characteristics during design and operation. Primary sources of mechanical excitation, reciprocating compressors and positive displacement pumps, rotating machinery and structural coupling. Reciprocating compressors and positive displacement pumps are major contributors to mechanical excitation in piping systems. These machines operate by cyclically compressing or displacing fluid, generating alternating forces that propagate through suction and discharge lines. The dominant excitation frequencies correspond to the machine's operating speed and its multiples, creating a rich harmonic spectrum. These harmonics can excite multiple piping modes, especially if the system lacks adequate stiffness or damping. The severity of vibration depends on machine size, operating pressure, and speed. API 618 and API 674 provide guidelines for pulsation and vibration control in reciprocating compressors and pumps, emphasizing the need for pulsation dampeners, proper support design, and dynamic analysis. Failure to address these issues can result in fatigue cracks at welds, failures of small bore connections, and damage to instrumentation tubing. Engineers must consider these factors during design and maintenance to ensure long-term reliability. Rotating machinery such as centrifugal pumps, compressors, and electric motors can induce mechanical excitation through imbalance, misalignment, and rotor dynamics. Although the vibration levels are generally lower than those from reciprocating machines, they can still be significant when transmitted through shared supports or structural frameworks. For example, a pump mounted on a skid can transmit vibration to adjacent piping via common supports, even if the piping is not part of the pump circuit. This structural coupling effect is often overlooked but can lead to unexpected vibration problems. Preventive measures include isolating machinery using anti-vibration mounts, ensuring proper alignment, and avoiding shared supports between vibrating equipment and critical piping. Dynamic analysis during design can identify potential coupling paths and allow engineers to implement corrective actions before commissioning. Impact on piping integrity and fatigue risks, consequences of mechanical excitation. Mechanical excitation can lead to severe integrity issues in piping systems. When resonance occurs, vibration amplitudes increase dramatically, causing high cycle fatigue at welds, small bore connections, and supports. Fatigue cracks often initiate at stress concentration points such as branch connections or welded joints. Over time, these cracks propagate, resulting in leaks or catastrophic rupture. In addition to fatigue, vibration can cause fretting at supports, loosening of bolts, and damage to instrumentation tubing. The economic impact includes unplanned shutdowns, costly repairs, and production losses, while safety risks involve potential hydrocarbon releases and hazards to personnel. Understanding these consequences highlights the importance of proactive vibration assessment and mitigation strategies during design and operation. Preventive measures and design consideration strategies for mitigating mechanical excitation. Preventing vibration issues caused by mechanical excitation requires a combination of design, operational, and maintenance strategies. Key measures include avoiding resonance by ensuring excitation frequencies are at least plus or minus 20% away from piping natural frequencies, adding stiffness through supports and clamps, and using pulsation dampeners for reciprocating machines. Isolation mounts can decouple machinery from piping, reducing transmitted vibration. Proper alignment and balancing of rotating equipment minimize excitation forces. For critical systems, dynamic analysis using finite element modeling and pulsation studies is recommended to predict vibration behavior under various operating conditions. Compliance with standards such as API 618 and API 674 ensures best practices are followed. Regular inspection and monitoring of vibration levels during operation help detect emerging issues before they escalate into failures. Industry standards and best practices, API guidelines and engineering recommendations. Industry standards play a crucial role in managing mechanical excitation risks. API 618 provides detailed requirements for reciprocating compressors, including pulsation control and vibration analysis. API 674 addresses similar concerns for positive displacement pumps. These standards recommend the use of pulsation dampeners, proper piping layout, and dynamic analysis to prevent resonance and fatigue failures. Additionally, good engineering practices include minimizing unsupported spans, avoiding shared supports between vibrating equipment and critical piping, and implementing robust inspection programs. Adhering to these guidelines ensures compliance, enhances reliability, and reduces the likelihood of vibration-induced failures in process plants.